So welcome again. So week 2 topic, I'm kind of going to continue for the first 4 weeks at least, this dive into string, the fascinating world of string algorithms. I think we started with the Z algorithm, Gusfield Z algorithm, and to just recollect it, I'm not going to revise the whole thing, but you recollect it. It was an algorithm to pre-process any given string. It was not an algorithm about anything as such, but then you could use that pre-processing step to drive a variety of string-related algorithms. And in fact, if you go to the tute this week, and the tute in the labs and tute would start this week, so you have a 1-3-hour block in which you would cover both tute and track, you would see that Z algorithm is applied to a whole class of string problems to do them efficiently. But at the very end, I kind of told how you could actually use, in the last 5 minutes really, the mic drop moment from the last week's lecture was how do you do exact pattern matching in time proportional to the sum of the pattern and text length. Usually pattern lengths are small. You're searching for small queries over a large, ginormous text. So the dominating aspect, it's linear in the time proportional to the text length. And what was a Z data structure? It's an array. And at any position I, what does it store? It stores the longest length of the substring starting at position I that matches the prefix. Okay, do you remember that, everyone? So the longest length of the substring starting at position I. So what if a string is S, Si, Si plus 1, Si plus 2, how long can you extend that substring so that you get an equivalent match on the prefix side? Okay, with that sort of reflection of what we done in week 1, we'll jump into this classical proper linear time, the algorithms that actually arose to solve a specific problem, which is to do linear time pattern matching, Boyer-Moore and KMP. Now, in fact, Boyer-Moore, if you ever run grep on Linux machines or anything like that, you would have the grep is basically the sed equivalent of G, RE, and P, globally search for a regular expression and print, basically. And the internal algorithms that they use, nut and bolts, lot of search engines, on a computer, anything you search for text, implements variations of Boyer-Moore. KMP is more sort of at the very end, I'm going to talk about KMP, which kind of reflects on an algorithm that arose around the same time, probably not as relevant as Boyer-Moore. But in doing so, I'm going to give you a modern treatment, or at least the lecture is going to talk about the modern treatment of Boyer-Moore and KMP, where we're going to use Z algorithm as the wrench to sort of drive the shifting that's there, to shift pattern under the text efficiently. Okay? If you did the original jump tables of Boyer-Moore or KMP, it would give you an equivalent speed up, but then it's far more easier to implement, at least the case I'm going to make for all of you, it's far more easier to do it using Z algorithm as your basis to drive the shifting of pattern under the text. Everyone clear with the agenda? Okay, so let's jump in. I'm going to ignore the recap slides. We'll go into Boyer-Moore directly. Now, how does, I'm just going to keep using. The whiteboard looks like it worked reasonably well. I have to zoom in. So the slides that you have will double up as your reading material. I don't want to slavishly talk to the slide. I'll take the liberty of talking the essence of the slide on the whiteboard so that we can go back and forth from the slide and the whiteboard during the lecture. Yeah? So really, Boyer-Moore algorithm for pattern matching has 3 main ideas. The first idea is right to left scanning. I'll just enumerate them and then talk about each one of them as we chug along. So first one is right to left scanning. Second one is the bad character rule. And third would be the good suffix rule, okay? Now, what does all that mean? So if you have your text, I'll call them 1 to n. Obviously, patterns often smaller. I'm going to write a pattern as a small dash. Text is a big line. So you start by, you're essentially moving the pattern left to right. So pattern against the text is shifting left to right, like you would intuitively do if you're doing a naive algorithm, isn't it? Okay? It shifts left to right. But so essentially, one iteration could be like that. You could get a big jump. The second iteration would be like that. Third iteration could actually be completely, so same size. So that's first iteration, second iteration, third iteration, fourth iteration could be something like that. So you're shifting left to right. But in each iteration, let's take some iteration in the middle, 1 and m. So the pattern is in some iteration while you're shifting. In each iteration, the comparison is not from left to right. The comparison of opposing characters is not left to right. If you're writing a naive algorithm, that's what you would do, isn't it? So you would write a comparison from left to right. But then Boyamo says, well, let me actually do something different. I'm going to first match the last character of the pattern against wherever the text is. So let's assume that you are in some iteration where 1 to m is opposing j to j plus m minus 1. So basically there are m characters in the text starting at position j that you're comparing against 1 to m. The comparison starts from right to left. Have I convinced you what right to left is? It's a fairly simple idea. First idea is basically facile. We don't have to, but as long as you understand that every iteration, the pattern is still moving left to right, but then the comparison of characters in each iteration is right to left. Okay? Shifting left to right, but comparison in each iteration right to left. Okay. Now, we had these two other rules where we said this bad character shift rule and good suffix shift rule, or bad character rule or good suffix rule. Now, what is a bad and a good, what's a character and what is a suffix here is what this comparison, right to left. As you're comparing, it turns out that you will have a certain number of matches. So you keep comparing until things match. This character matches with this character, this matches character matches with this character. And at some point, you might get a mismatch where, is it big enough for you to see, or should I write it a bit bigger? So I will draw that in red. So if there is a character x that is, you kind of did a right to left scan, it stopped. You can't no longer extend because this characters don't match. Then in that iteration, in that specific iteration, you have x in the text as the bad character that stopped the matching to proceed all the way to the left. It was a bad character. Had it been a good character, you would have matched and went to one letter before that. Is that clear? So that's the bad character in the text. Okay? And then what's a good suffix? Now, if you look at the characters that are to the right of the mismatch, is that the suffix of the pattern? So let's say that the position there was k. 1, k is where the mismatch happened. M matched, m minus 1 matched, m minus 2 matched until k plus 1. So k plus 1 to m, is that not a suffix of the pattern? Yeah, suffix of the pattern. So do you agree that because these characters match the opposing characters in the text, this suffix is a good suffix of the pattern in that iteration. So the notion of a bad character and a good suffix is a function of the iteration in the boy more. Okay? So that's going to be a good suffix. Now, what's the motivation of bad character and good suffix shift rules? Now think about, you are the chairperson of a committee. You have two experts. One expert is a bad character expert. The other person is the good suffix expert. You want to ask the committee, how much do I shift the pattern safely after the current iteration? After I finish my current iteration, how many characters do I shift by? Now, committee member 1, the bad character expert, says, oh, shift by 3 characters, let's say, okay, some number. Some number greater than or equal to 1, okay? And less than or equal to m, right? So you can say, well, you can shift by 1, that is a naive shift, or 2 or 3. Let's say that the first bad character expert committee member 1 said shift by 3. Now, committee member 2 is a good suffix expert. He says, well, actually, you can shift by 4. Now, as a chairperson, you know that both of them are honest. They will never mislead you, meaning that if they gave a number, it would always be safe, meaning that you wouldn't miss anything in between shifts. Does that make sense? So you're shifting, and you would never miss something in between the shifts. So going from one iteration to the next, you never have to worry taking the advice of either of the bad character shift expert or the good suffix expert that you missed something in between, in the gaps. Now, if you are a chairperson, one says 3, other says 4, who would you listen? And both are honest. You obviously would go with the best of both, isn't it? Well, bad character had an opinion, but he was right. Good suffix had an opinion, she was right. And then you would basically say, well, what's the best version of the two? I'll go with, both are safe, I'll go with something that is the best of the both choices, right? So that's the agenda. Overall agenda is, I'm going to show you how do you shift using bad character rule, 1 or more positions depending on the scenario in that iteration. Separately, I'm going to show you how do you shift based on the good suffix, 1 or more position based on the scenario. And then at the very end, you have to say, well, bad character says shift by some number of characters, good suffix says some number of characters, I'll take the best of the both. Clear? Okay, agenda is pretty clear. Check along. So I'm going to, I've already told you what a right to left scan is. I'm going to go straight into. So right to left scan defines a bad character in each iteration and a good suffix. So bad character is in the text, good suffix is essentially in both in that iteration. So it's a good suffix of the pattern that also matches a block in the text. Okay? Now, let's first focus on the bad character rule. So I'll just clean up the board for a bit. So now we are in a pattern, 1 to m. So let's assume that there was a mismatch of some character x with some character y, and everything after those characters matched. I mean, I like giving names to substrings. So alpha is a substring in the text that matched the suffix of the pattern. And the suffix starts at position k plus 1 from the start. So 1, 2, 3, 4, k plus 1. And the mismatch is at position k. Okay, that's the setup. Now we said that initially we only care about bad character in the bad character shift rule. So we are only focusing on x. Okay? Now, how do I use the bad character shift rule to shift knowing that that position is X? Because I have done the matching. I came here, there was a Y, but that character is an X. Okay? So the idea that Boyer-Moore initially came up was that now in my next shift, if any other character other than X is in the pattern, it will be a mismatch. You have a shift. If any other character other than X is at that position right there. So whatever position K in the pattern, so this will basically be, so that's J plus M minus 1, that will be that M characters. So K characters from J is an X. So K characters from the start would be Y in the pattern. It's a mismatch. If I let's say shift the pattern rightward, so that's a pattern. If I shift the pattern and the pattern now was 1M, the corresponding position out here after the shift, if it's anything other than an X, it has to be a mismatch, right? Okay, so obviously I have to find where X's are, or where that specific back character, this back character is X in the text. Where are the other X's in the pattern? Now, what are the scenarios? Scenarios is there are no X's in the pattern because it's a specific character in a string, and you have drawn two strings, one's a text, one's a pattern, so X need not exist. So if there is no X's in the pattern, what would you do? You just shift across. Across what? Across the point of the current mismatch. Yeah. So if you found an X, let's assume that you found an X somewhere there. Okay, there was an X somewhere there. Your shift would be such that these characters have to align, right? Let's draw M1, and that's in. So you're shifting such that, so this was a previous state, X was here, and you would essentially see a Y and an alpha for sure, because you have just shifted the pattern, and you're making sure the X, the bad character in the current iteration, is lined up with the X, right? If you had a single X in that form. I'm just enumerating the scenarios that could happen. Now, is everyone clear what I'm trying to do here? Now, once I shift it, then what? Okay, I've shifted it. Let's assume that this was safe, and we'll see whether it's safe or not. In fact, I'll get you to reason that in your tutes next week. If you actually go up to your week 3 section, your next week's tute is already up, so you can think about why these shifts are safe, and there's a beautiful proof by contradictions that we will explore in the tutes next week, thinking about why it is safe. You will never miss, actually solidify mathematically why that shift is safe. Now, once you've shifted it, then what? Okay, we'll see. There's a few more scenarios to consider, but let's jump forward and say, well, it's safe. You've shifted it. My iteration sort of did not, at position J of the text, gave me a bad character, did not basically find an occurrence, so I shifted it. I know it's going to be safe. That's the next start of a next iteration. You would again, so now what you will have is a comparison, it's a right to left scan until you find its mismatch. It will then give a new definition of a bad character for that next iteration and a new good suffix. Is anybody confused about this? Please feel free to stop me if there is some part that's not clear. If you want me to repeat something, this is the time for you to tell me that I'll repeat something and I'll do that. So the idea is you're shifting. Bad character is shifting only based on the bad character in the current iteration. After you shift, you're back to square one. You are again doing right to left scan. It will define its own good suffix and a bad character. Bad character is always in the text. Okay? Everyone clear? Okay, so if that's true, then we'll go back to the original iteration, original scenario, where we are doing the comparison in that iteration. I showed you the case that when there is no x, you would shift across the point of the mismatch. You can move the pattern. If there is no x, then essentially, if there was no x, you would shift like that. Okay? If there was one x somewhere in between, you would shift such that that x is lining up the bad character. Now, what other possibilities exist? Can somebody think about it? It's early morning, you might fall asleep listening to my boring voice. Anybody else wants to participate about what other scenarios could happen? Feel free. Yes, sir. Which is a match? Everything matches, right? So we will hold on to that at the very end. But in terms of assume that there is a bad character, then what other scenarios can happen? So the scenarios we explored, there are no bad characters in the pattern. There was one bad character in the pattern. The generalization is there more, right? The more bad character in the pattern. So let's assume that you had, I'll just draw two x's, just in case you could have two or more, yeah? Which x do you shift by for it to be safe? The rightmost one is a hypothesis. Anybody else want to think about it? Not the leftmost one. Actually, to make it interesting, let's basically have another x there. 3 x's. It's still the rightmost one for you? And not the left, not the one in the middle. Anybody wants to challenge that hypothesis? Now, does somebody want to, the answer is correct, it's rightmost, but why? So whenever you have multiple x's, there's still one more scenario to handle, but when you have two or more x's, you always choose the rightmost x in your pattern. So this is x is a bad character in the text, and you're saying, okay, where are the x's in my pattern? And if I have a few, you'd always choose the rightmost one. Okay, there's one more scenario we'll enumerate, but the question is, why is it rightmost one before we go to that scenario?
For me, I feel like also use right to left if we're going to find the pattern, matching pattern. So if you from the right to the left, that's the first time or first occurrence in mind the
yeah.
match. So in this area, it should be from the rightmost one.
Sure. I think you are on the ball. I think you've said that intuitively. But yes, sir. I think you're channeling the last scenario in a bit. But let's assume that all the x's were were before alpha. Okay, wherever the alpha was, all the x's were before the last character is what happens when the x is in the alpha. Okay, that is basically if what happens if x is beyond the point of mismatch. Okay, so but right now assume that all x's were before the point of mismatch. The position k is the mismatch in the pattern, and you're saying that I want to shift to the rightmost occurrence of the x in the pattern. The question is why. Now, think about if I chose to, let's put a subscript of this x, actually x1, x2, x3. They're all x's, right? x1, x2, x3 are all x's. They're instance 1 of x and instance 2 of x and so on. If I chose to move to the leftmost x that you see on the screen, what would be the scenario? I will shift such that my pattern will have x1 opposing the x here. If I did x2, I would shift so that I will have x2 opposing the x here, the second instance of the pattern. Now, if I had the third one, I would have x3 opposing x. Now, of the three choices, at least in the illustration, the most aggressive one is the leftmost, and second most aggressive shift was x2. The least aggressive, the most conservative shift was x3, isn't it? Always has to be if the rightmost occurrence of the character with respect to the position of your current mismatch will always give you the most conservative shift, and hence it would be the safest. I mean, this is an intuitive way of saying it. In your lab, I'll get you to do a proof by contradiction thinking. Your tutors would help you to reason this much more formally using a proof by contradiction. Let's assume that the assumption is that if you shift so that the rightmost occurrence of x that is before a point of mismatch is aligned. So like this one, not these first two, but if you are shifted such that the rightmost occurrence, which is the third instance of x, is aligned, we know it's safe. I'm telling you that it's safe. In the lab, you would have to say, do a proof by contradiction, and say, no, it's not safe, which means that you might have missed something between the two shifts and see if there is a contradiction that arises. In fact, the contradiction would be the contradiction to the definition of the rightmost occurrence of x. The rightmost is a very tight statement, isn't it? It's a mathematically solid, strict statement. Now, if you assume that proof by contradiction is always to say, well, maybe that statement is wrong, and then if you basically get a contradiction, then you have reduced that contradiction to an absurdity. Okay? Reducto or ad absurdum, as they would call it in math. So you basically reduce it to absurd. If that assumption is, that's what proof by contradiction is, something that Euclid used so many millennia ago to prove things like why are they infinite primes. So it's using age-old techniques to reason why this shift is correct. So are you with me so far about what the shifts are? Now, one last scenario, and I think it came up with the other gentleman's suggestion. What happens now? All the thing is there. Let's assume that there was a fourth instance of x, but this time here. On the right of the point of mismatch in the pattern. What do you do then? We said shift by rightmost instant. Let's assume that we shifted that. What's going to happen? If we blindly did what we were doing in the previous instance, what would happen? Can you see what will happen? The pattern would go backwards, right? But do you want to go backwards in this algorithm? No, we've already done that. So the idea is that if you were doing a bad character rule blindly, okay, if you're just doing the bad character rule blindly, then you would essentially get to in certain scenarios, because this is a function of x. X is in a a specific iteration, a specific character in the text, right? And these keep changing in iteration after iteration, and some iteration you might get a sense where if you're doing just the bad character rule, the rightmost occurrence could be in the part that you've already matched, a good suffix, which means that when that happens, if you were just using a bad character rule, then you have to shift by one position, naive. So if it's beyond this point, you have no other choice but to shift by just one position, the naive shift. So it's always going to be some. So we have to now solidify this thinking about how do we implement it. Okay, let's basically go to the illustration. Okay, so we saw a text, a pattern. That's a bad character because all these things matched. That's a bad character. The rightmost occurrence of the pattern in the text happens to be the first character in the pattern. So you shifted by two positions, and that's one iteration. And then how do you pre-process? Now, question is, can bad character be different in different iterations? I've already said that, right? Every iteration gives you your own bad character. So if it's different in different iterations, so what are the possible bad characters you could have? It's basically whatever characters that the strings are being drawn from, isn't it? So, and often it's a very small set. If you're if you're doing pattern matching, your alphabet size is short, okay? If you're doing plain text, alphabet size is plain text ASCII. Okay, ASCII 7-bit is 127 bits. Okay, sorry, 7 bits is 127 characters, 8 bits is 256 characters. There are only 256 possibilities if you're doing plain text ASCII on a computer. If you're doing English, maybe you have 26 uppercase, lowercase, and some special characters on a standard English text. But my point is that alphabet is constant. All you have to do is, even before you saw the text, you want to pre-process the pattern for the rightmost occurrence of each of the characters in the alphabet in the pattern. You can do it even before seeing the text, because the bad character is going to be one of those characters. Okay? Some of them would be missing, isn't it? So your pattern might not have everything. For instance, in that example there, you have the pattern was T, B, A, P, X, A, B. Let's assume that you had an alphabet of only 26 lowercase characters in English. So you have an array that is storing the rightmost occurrence of each character X. X is a variable that's coming from each character, that's taking a value of each character in the alphabet. Now, have I seen an A in the pattern? Yes. What's the rightmost occurrence of that A? It's at position 6. Can you see that? Have I seen a B in the pattern? Yes, there are two instances of B at position 2 and position 7. What is the rightmost occurrence of the B? It's 7. Have I seen a C in the pattern? Well, there's no C in the pattern, so because I'm counting from 1, so it's basically going to be 0, yeah? There's no rightmost occurrence is 0. Is everyone clear about what that table is doing? Have I convinced you that this is going to be a pre-processing on the pattern? You could construct this without even seeing the text. Yeah? Because it's a function of the pattern. Okay? Although the bad character is defined from an instance in an iteration in the text, the X's get a meaning in a specific iteration when a pattern is being compared with the text. You could pre-process for all possible ways in which you have X's in. Give me 1 second, I'll close the door. So yeah, you could have all possible ways in which you could see what possible values X can take before you even see the text. And if I want to solidify what the shift rule was saying, you could do that pretty straightforwardly. There's nothing, you just need a space which is equivalent to the size of the alphabet, scan, read every letter, and then update. You could do it in linear time, in time proportional to the pattern length, so OM time, and O, the alphabet size space. Okay? Size of the alphabet is always a constant, so you could say that it's a constant space. So you don't have it, in any practical purpose, you would never have a variable sized alphabet. Okay? You would basically have a constant size alphabet. Now, shift rule, take care. Okay, shift rule, I mean, I'm just going to go to the part, I've already told you what all these things are. Okay, the jump rule is here. So it is saying that the jump rule is, I'm using R. Somebody say anything? Okay. All right, fair enough. Okay, thanks Siri. Am I right? That's all bullshit. So, right, R of X is basically showing the rightmost occurrence of any back character. Now, K is the position of mismatch in the current iteration. So, I'm going to shift by K. I'm going to shift by K minus Rx positions, because that's basically the width, number of characters to line up, so that I can shift such that the rightmost occurrence lines up. So that's going to be K minus Rx. The value is already being computed. You know what K is. K minus Rx tells you how many characters shift by. The only catch is that last scenario. What happens when Rx is greater than K? What is K minus Rx? When Rx is greater than K? If it's an alpha, it will be negative, isn't it? That's what we saw. We're going back. When if it's negative, you say, well, if it's negative, just use 1. Okay? It's going to be max of 1 comma K minus R of X. So that 1 telling you that if the rightmost occurrence is beyond the point of mismatch, don't go back, just use 1. Okay? Have nailed this intuition for you? Okay, now, can you make it a bit more, can you extend this bad character rule in some special way so that we never ever get the scenario where the rightmost is greater, Rx is greater than K? How can we tighten the definition of the bad character, what we are searching for, so that it's always moving forward without having to do the max of 1 comma that?
Will it be the rightmost character to the left of the good suffix?
Brilliant. Thanks a lot. Very nice. So the answer there was always pre-process the pattern for rightmost occurrences to be before the point of the mismatch. But there's a problem. Okay, it's a great answer, but there's still something more that we have to do. Now, do you agree that the point of mismatch is a function of the text and the iteration in the text, right? Alpha could be in one iteration, could be 0, or it could be 1, or it could be 2. So that gives you different values of K. So you have another degree of freedom. One degree of freedom is what is the bad character. The other degree of freedom is where is K. So K can be at what position? It could be at M or M plus 1, M minus 1. Sorry, I'll say that again. It could be M, it could be K could be M or M minus 1 or M minus 2 or M minus 3 all the way to 1. If it's you could have, in the worst case, you would match M all the way to 2, and then the mismatch can happen at position 1, and it defines its bad character. So now you have 2 degrees of freedom. So we are now talking, see the point there? So you could have x being the character to the left of the point of mismatch, but the left of the point of mismatch, the mismatch itself has a degree of freedom. It can be m or m-1 or m-2 or m-3. So you will have to pre-process, instead of an array Rx previously, you have m cross the alphabet size. So previously you had an array of Rx values over the alphabet range, isn't it? For A, B, C, D, what is the... now you could say, if it's A and the mismatch point is position 1, what would be the rightmost occurrence of the character to the left of the first one? That doesn't make any sense, isn't it? Then the second one, if let's say that you had A to the, and the mismatch was at position 2, what is the rightmost occurrence of A? That is to the left of position 2. What's the rightmost occurrence of A? To the left of position 3. And that is you can actually build an extended version where that dimension would be the size of the alphabet. Okay, let's call that alphabet some chi or something like that. And then out here, so maybe I'll write it as A, B, some x. Let's say Z, let's say their alphabet was English letters. It could be any alphabet you choose. That's the column side. The row side could be 1, 2, 3, 4, 5, all the way to M. So it's going to be an size of the alphabet times M table, a 2-dimensional table, right? So you could have these R x values as a function of k, 2 degrees of freedom. X would be the character column, or k comma x if you want to write it this way. K and x. K is an integer, x is a letter. I'll just put it like that. So when you say what is the rightmost occurrence of any character to the left of a given point of mismatch, you look up into this table and then get a number. Can you see that? I'll just show you a table, then it'll all become pretty clear, okay? Give me one, we have covered all this, don't worry. Extended bad character. Okay, I'll just show you this table. Whatever I've skipped is something I've covered on the board anyway, but take a look at that table, stare at it. Columns are letters, rows are positions. Even before you see any text, you could pre-process this extended table for all possible ways the character can change and all possible ways in which the mismatch can happen. Okay? Are you happy with that table there? Does anybody have do you want me to clarify anything about this table? Okay. Anything specific? I'll just take one example. X, right? So position X, what is the rightmost occurrence of X if the mismatch was at position 1? Well, there's nothing. What's the rightmost occurrence of X to the left of position 2? It's 0. What's the rightmost occurrence of X to the left of position 3? It's 0. Right? What 0 implies it doesn't exist. Rightmost occurrence of X to the left of 4, left of 5, and then left of 6. Suddenly you'll start seeing that the rightmost occurrence of X to the left of 6 is position 5, isn't it? Can you see that we've got all zeros, and at 6 you got a 5. Yeah? So if you just stare at this column here, at position 1 it's 0, position 2 it's 0, position 3 is 0, 4 is 0, at 5 is also 0 because you're looking at the left of that position. And then at position 6, what's the rightmost occurrence of X? That is basically a 5. At position 7 it's still 5. Okay, let's take a more interesting example. Let's take the bad character as A. What's the rightmost occurrence of A to the left of T? Is 0. So you can look at this column as I'm going along. What's the rightmost occurrence of A to the left of B? Is 0. Left of 3, or rightmost occurrence of A to the left of 3 is still 0 because we are not counting that position. 4 would be 3. At position 3, you saw an A, didn't you? At 5, what is the rightmost occurrence of A to the, 3 to 6, it's still 3. But at 7, well, I got a new A, it's 6. Can you see that? So, and do you agree that I can pre-process it quite trivially before I start? Now, if you did that, in any iteration, you are saying, if the mismatch was at position K, so in any iteration, the mismatch was at position K, you got an X as a bad character. You could just say, okay, look at the kth row and the xth column, and then what is the number that gives me R of that bad character. Yeah? And you shift by that. Are you all with me, or am I? Okay? All right, so with that, so you don't need a max of 1 comma that. If you had an extended table, you just have to plug in the value. It will always give you a value of 1 or more. Okay? All right, so we are done and dusted with the first committee person. Yes? Good question. I think it's a question that's on the online forum, or those on the online side of things. The question is, why would be a 2D array better than 1D? The only reason is that in 1D, you get to a scenario where there would be a character, a bad character in the good suffix, which with no other character before the point of mismatch. Let's assume that there was an X only out here, and there's nothing before. So everything else was, if you're seeing my screen, those one who has asked this question, so let's assume that you got a X and a Y, that's a point of mismatch. There was only one X that is to the right of the point of mismatch. You would, with the single array version, the array version without the standard bad character rule, shift by 1. But if you applied the extended bad character rule, you will shift by everything before because you haven't seen any X before. Okay? You will actually be much more aggressive in your shift in scenarios where there's only one bad character, and that happens to be in the good suffix to the right of the point of mismatch. Okay? Does that? Think about it. If what I've just said, what would happen if you just had one character that's to the right of the point of mismatch? In the regular bad character rule, it's just shift by 1 because it's going to be max of that. But if you did a extended bad character rule, the position K, what is the rightmost occurrence of X to the left of that? Well, it's 0, which means that you have to shift by K minus 0. You're going to shift by K positions rather than 1. So that's the advantage. And you might say, well, isn't it a space-time trade-off? Yes and no, because the pattern size is small, so is the alphabet size compared to a text. You could have a text that is billions of letters long. You would still have the table defined by the pattern size and the alphabet size not changing with the size of the text. Okay? It's not a big deal. You can be a bit more efficient in how you store them with some lookup trade-off. So if you have a table, your lookup is always going to be constant time because you know a row, you know a column, you'll look up in constant time. If you had a more fancy data structure, you would have less space than, in fact, you could actually write the two-dimensional version, 2 degrees of freedom version, the extended bad character rule, in OM space. So the space here is m times the alphabet size, but you could actually do it in OM space, but the recall of that would be not constant time. It depends on the data structure that you do. So it'll be, you could actually do it in log m if you did it in one version of it. Okay, so it would basically take in log m time to search for this if you have a fancier data structure other than a standard two-dimensional table. Okay, good question. All right, so with that motivation for bad character rule, we'll shift our attention to the remaining part of it. Okay, one expert said something, we have justified what the expert has to do. So now is the good suffix. Now a point of view of thinking is now that's a text, 1, n, and now you have a pattern, 1, m, and there is some good suffix, alpha, before you saw the the mismatch. Yeah? Okay, your focus is now on the good suffix alpha rather than the bad character. Okay, alpha is going to be a function, the good suffix is going to be a function of, wouldn't good suffix be a function of the pattern again in a certain iteration? Pattern and the text, sorry, in a pattern and the text in a certain iteration. So each iteration might have its own alpha, definition of alpha. Now, the idea here is to pre-process your pattern with respect to any possible alpha that I can get. Remember, alpha is always a suffix. How many suffixes do I have in a pattern of size m? 1 to m is the pattern. So what are the suffixes? 1 to m, 2 to m, 3 to m, all the way to m to m. So there are going to be m suffixes, isn't it? So there are only m possible ways that alpha can be defined. There can't be more than that. Now, what are the scenarios that can happen in any iteration? Okay, can somebody help me with the scenarios this time? Yes, ma'am. Okay, alpha could be equivalent to 0 to length. So if alpha is equivalent to 0 in length, what rule would you have to use? Or let's assume that, so when alpha is 0, I'll remove this for the moment. If alpha was 0, length 0, which means that the very first character was a mismatch, right? Very first character was a mismatch. So you have no other choice but to use a bad character rule straight away. Okay? So that's good scenario 1, that's perfect scenario 1, but it kind of falls back to a bad character rule. Okay? You don't have to shift by 1, you could shift by whatever that bad character allows you to shift by. Okay? What happens if you had alpha greater than 1? Greater than 0, greater than or equal to 1. What are the scenarios that could happen? So remember how we reasoned the bad character rule? We said, what if there were 1 instance of the bad character, or 2 instances of the bad character, or 3 instances of the bad character, and so on. So it's the same kind of thinking. So let's assume that there were no instances of alpha in the pattern. Alpha never appeared. I mean, when I say no instances beyond the one in the suffix. You have never seen alpha anywhere else. Okay, there has to be 1 instance because you have defined alpha. So if you didn't see an alpha, what would be a safe shift? And why? Why would that be so? Why would it be safe? Intuitively. I think again, you have to use the proof by contradiction to make this fully tight, watertight in your tubes, but why? Yes, ma'am.
Because if you know that there's no other alpha in the pattern, then you know that there's no other way it could.
Yes. Very nice. So, in the other way of saying what the answer was in the audience was that if there were no alpha, any other shift, let's take a shift like this, some arbitrary shift, that region will be some value not equal to alpha, which means that it's going to be a mismatch. So that shift will bound to be a mismatch. What's the goal of shifting? Is to find matches, isn't it? Find occurrences. When I know that I'm going to get a mismatch, that position is unnecessary for me to shift by. So really, you will have to shift across. So you're safe to shift. We'll see there's one wrinkle about what the shift should be. There's a small wrinkle. We can safely shift. I know that you can't just simply shift it beyond the end of the pattern. I'll tell you why. There's a small wrinkle. But it's clear that you can shift anywhere, so that if that's the position, anywhere beyond that position, anywhere to the right of that position. That position is K. You could shift it to a position beyond the point where they kind of had that instance alpha matched with alpha. So this alpha matches with alpha. So the point is that you have to shift it. You have to shift it in such a way that it is. Oh, it says mismatch is K. Sorry, mismatch is K. That's K plus 1. So you have to be to the right. You have to shift it to the right of the point of the current mismatch. Okay. I'll tell you why it's not to the right of M in a bit when we chug along. Now, so that's scenario 1, okay? Scenario 1, if you didn't have any instance of alpha, you have to shift it to the right of position where you had the current mismatch in that iteration, okay? Which position it is, we'll clarify in a bit. What's the second scenario? Let's say that you found an alpha, instance of alpha like that. What do you do? Yeah, obvious, right? So what do you do when you have an alpha, one instance of alpha beyond the good suffix? So you saw an alpha before that. Shift such that so you're sort of lining these up. You're shifting such that that alpha is now opposing these, and these are going to be equivalent. And then what do you do? I mean, I just want to keep reminding, once you do that, you start a new iteration. Now everything's scratch. You have to start matching right to left, and it defines an alpha, a good suffix, and it defines a bad character if you didn't find so you would only not find a good suffix and a bad character if you match the whole thing. Okay? When you match the whole thing, we have to handle that scenario separately. Because there's no bad character, there's no good, I mean, the good suffix is itself, right? So the whole thing matched. And that's what you're looking for in this algorithm. We'll handle that scenario at the very end as well. So is that clear? So when you have an alpha, so what happens now if you had maybe I'll draw a longer, but that's Y. Let's say there were two instances of alpha, instance 1, instance 2, beyond the instance of the good suffix. Which one would you shift by? So that's some position P1, that's some position P2. Should P1 line up to that position or P2 line up to that position? Anyone? So I'll draw both of them. So if you did P1, so that's M. If you did P2, so option 1, option 2, which one would you choose? Anyone? And the reason being, who said that? Yeah. Yes. So it's basically going to be the most conservative of the shifts. Again, the same discretion that we had with good suffix, we're applying on, on bad character, we're applying on good suffix. So one would give you an aggressive shift, and the other would give you the least aggressive shift. So you always have to do the rightmost occurrence of alpha to the left of the good suffix, right? So good suffix is alpha. Whatever the alpha is defined, you want to shift by to the rightmost instance of it. Okay? If you had you could have more of them, it's the same thing, isn't it? So if you have alpha out there, it's the first, second, third. So you would have, of the 3 options, you would have to choose the rightmost occurrence. So which means that wherever you are, you would always shift by the most conservative shift, because if you shift to the rightmost, you are ensuring that so ensuring that the alphas line up after shift, and then that would be the most shortest shift. How much did you shift by? It's basically shifting by such that this instance takes the position of the where the good suffix is. You're shifting such that the least amount of shift that you need to do such that the alphas line up, and you will never miss anything in between, because there's no other alpha. Any other shift in between would have been a mismatch. Okay? Now, the big question is, okay, with that intuition, there is a small, and this is where Z algorithm is such a brilliant thing. Okay? I'll draw this. I'm going to go back to that scenario where let's assume that you had an alpha, only one instance of alpha. Should you care about, so let's say that this character was also y. Would you still prefer to shift such that the alphas line up? Why? Because it's going to be a mismatch again, yeah, obviously. Because if I shifted, I would get a scenario where I would get one M, an alpha here, and a y here. It will, no matter what, let's assume that there could be a right to left scan that could have ended prematurely, because you only know the certainty that alphas align, and then now you got to a point where if you ignore what's before alpha, alphas line up, but then let's assume that you did a right to left scan, it reached alpha, it match, and once you come to that position, you're doomed to fail, because you didn't care about what preceded alpha. So if I have to find the rightmost occurrence of alpha, it has to be a rightmost occurrence of alpha, so there could be multiple. So rightmost occurrence of alpha such that the character before alpha is not equals to y. Okay? Now this is getting very interesting, because Z algorithm will always give you something like that, isn't it? Except that the whole reasoning about Z algorithm is match of a substring with a prefix, not a suffix. And it says that what's the longest match of a substring that matches the prefix such that the character afterwards will never match. The character after a Z box will never match, right? So because if it matched, then it would be longer. The notion of the longest substring comes from the fact that wherever there is an equivalence, the next characters don't match in the Z thing. Now, however, the logic here seems to be a bit inverted. We want to find out the rightmost occurrence. We want to find the first rightmost occurrence. Okay, that's a new wrinkle that we haven't seen in Z. And then it says that the relationship is between a good suffix and a certain substring. So alpha is a substring here. Is alpha a substring? You're trying to find out some match with of a substring with the suffix rather than the prefix, such that the character before, not after, is a mismatch. So what do you do to the Z algorithm to make that logic come clean? Does anybody have a white sheet of paper? Any white sheet of paper that I can borrow for a second? There's a reason why I need it. A4. Okay, a book is good enough. I'll give you just don't. Okay, if you want to tear it off, that's fine. I can give you the book back if. Thank you. Okay, I'm just going to so Z box, can you see that I'm drawing a Z box? So this is Z algorithm. Now, if I inverted the Z, the match of the substring is with the suffix, and the character after now becomes before, isn't it? So all I'm trying to do now is to use, the reason I needed a paper is I couldn't have inverted the board. So all I need is essentially a pre-processing of the pattern to find all possible alphas that appear somewhere else, that matches a substring in the pattern such that the characters before are different. And in that, I want to find the rightmost occurrence. If there are multiple alphas, so let's say there are multiple alphas, I want to find the rightmost occurrence. So I'm just going to go straight to the slide. I mean, everything I've said here has been covered. So that's basically saying that the alphas have to be matched and the characters before have to be different. Okay, that's what I've said here. If it's Y, this has to be a character that has to be. I've just formalized it with some variables and correct offsets. You can spend time in the during self-study to see why those numbers are correct, those variables. Why am I saying that the pattern P minus M plus K is not equals to pattern of K? Pattern of K is the position of mismatch, that's Y, and whatever I'm saying is that character before that equivalence of alpha is different, is what I'm saying there. Now, how do you go about implementing this thing? We're going to use the Gusfield's Z algorithm. So instead of finding Zi values with respect to the prefix, you want to find Z suffix of I. Okay, Z suffix of I is take your pattern, reverse it. Okay, reverse the pattern, compute the Z values. Okay, and that gives you Z suffix of I. Okay, same deal that you have done. Now, how do I use Z suffix of I to compute the good character rule? I'll just go to that. So say the definition, I want to find the rightmost occurrence of the rightmost occurrence of alpha using Z suffix of I. By the way, what's the complexity of finding Z suffix of I if M is the size of the pattern? It is OM time, isn't it? Because Z algorithm runs linear in the string that you give it. You have reversed the string. Reversing the string is linear. linear in the size of the pattern. And then once you reversed it, you want to run Z algorithm on that. That's also linear in the size of the pattern. Once you find it, I'm going to show you that a watertight. So this is Gus Field's watertight code. Essentially, good suffix is that loop from at line 7 and the 2 lines inside the loop. Everything before is just initialization. So what it's saying is go and compute Z suffix values. Z suffix values are, you have to do 2 things. I'm going to flag this verbally. Take the pattern, reverse the pattern, compute Z algorithm that you have implemented in the first week's content, and then you get Z values in the reversed sense. You kind of reverse now the Z array to get Z suffix of I. So you have to do 2 reversals. One's the reversal of the pattern to compute the Z array of the reversed pattern. But then the positions are with respect to the reverse, right? So you have to reverse that array back so that you get everything with respect to the original original pattern. If this is a bit too much technical detail, don't worry, we're going to come back to it in your tutes. You will get a second way of thinking about it. First time you do it, there are too many things happening, so you might not get the whole gist of what's happening. But to compute the good suffix, what Gus Field does is something very clever, okay? And really you could, the logic is between, in line 7 to 10, so it's a for loop. For loop is going from position 1 to m minus 1. Now why did it not go all the way to m? I'm counting from 1, not 0, by the way. Why did it go all the way from 1 to and stop at m minus 1 and not m? It's the same reason why we don't care in the traditional Z algorithm, which is relationship with the prefix, we don't care about Z1 value, isn't it? Z1 value is basically the length of the whole string. Now, in a suffix sense, it's a relation with respect to suffix. So you don't care about the Zm value because it's Zm value would mirror Z1 value in the forward sense. The reverse sense, you don't care about Zm value. Now, you're going from 1 to m minus 1, and then if you're going from 1 to m minus 1, what is this beast here? Okay, we'll see what that means in a bit. Okay, so this is pattern only 1m. You would have got some substring that matched alpha in the suffix side, such that the character here, so I'll just draw it alpha. If this was a character x, there's some character not equals x, correct? At that position, okay? By the way, I must also say that we want to, in the forward sense, it is always the zi value where the box starts. In the reverse sense, it's where the box ends when you reverse it. Okay, when you inverted that, where the box started, where I reversed it is where it ends, right? So when I saw an alpha that matches the suffix, I know the characters before are different by definition of Z boxes. Now, let's say that somewhere down the line I had a beta. Okay? What does that mean? It means that there was a Z box that matches the suffix, that is so the definition of a beta implies like that, isn't it? See what I mean? So you would have this match an equivalent size suffix in the Z suffix array. Now, if you're processing, if you look at that loop, P is going from 1 all the way to m minus 1. Let's say P was at position P1, okay? Remember, the value is always at where it ends, okay, in the suffix sense. So if P was pointing to P1, what are you interested in? You're saying that I want to find out what is the good suffix at that position? Because when you were using good suffix, what was the scenario? There was a text somewhere, alphas matched, x did not match with a y. Okay, that would have been a scenario, isn't it? You want to find out the good suffix with respect to alpha. Okay, where does alpha appear in the pattern? And that I want to find the rightmost occurrence. I don't just need one occurrence, I need the rightmost occurrence of it, correct? Now, if P was P1 and this P1 matches, so this alpha matches that, what would be that position with respect to M? We know that the length of that is Z suffix of P. Okay, P is P1, Z suffix of P would be the length. So this position would be M minus, let's call this length L, M minus L plus 1, isn't it? So if you went back, so if you look at the line there, M minus length plus 1 is what you're computing in line 8. So J would be the position, this position J, let's call this position J, is M minus L plus 1. Now, and then what are you doing? Good suffix of J, so if there was a good suffix starting at J, which is alpha, so by the moment you say J, J to M is a good suffix. Where did I see J to M in the pattern? It's at position P1 in my current processing. Let's say that there were another alpha somewhere, it could be any size really, and it's at position P2. Now when P comes to P2, previously you already computed good suffix of J as pointing to P1, but when you come to P2, you would say, what is line 8? J equals M minus whatever the length, the same length as you had computed previously, because that was what Z suffix of that position tells you. So plus 1, it would again point to the same position that you had previously computed when you saw the first instance of alpha, and then it'll overwrite it. It'll overwrite the value from P1 to P2. And when you process left to right this, you always would store the rightmost occurrence of alpha. Any alpha, in fact, because the alphas are being defined by Z suffix lengths. And as the lengths change, it is filling up different slots of good suffix, and in that, it's always overwriting to the rightmost occurrence of whatever alpha that you have defined. It's a linear time algorithm, okay? This is magic. Okay, so it's basically going to find the rightmost occurrence. Nothing more than that, you have a good suffix array created. Now, any questions? Perfectly fine if you're a bit unclear. So I must say that we are in advanced algorithm territory, right? In our journey, algorithm starts to become finer and more nuanced, but also more satisfying, intellectually very satisfying. That aha moment has to happen. But please don't feel discouraged if it doesn't happen the first time you hear it. It almost certainly didn't happen for your lecturer the first time he read it, or your teaching team when the first time they had done it. It's a process of spending. So now you heard the lecture, go back, revise it quite soon, so that in the context, and say, well, okay, Arun was mumbling about something about good suffix and rightmost occurrence, does it make sense? And it kind of clarifies a little more. Then you go back to the labs, your tutors would clarify a little more. The ultimate test is the great bullshit detector, as I said. The computer is a great bullshit detector. You have to then convince the computer that you really understood it. Okay? It's a satisfying process if you're doing computer science for the right reason. Okay? All right. With that sort of assurance that if you feel a bit confused, it's perfectly fine. Don't worry too much about it, but keep at it, and I'll open up a consultation slot this week. You can also come to the consultation to clarify. I'll advertise it on forum. Okay, so good suffix has been discussed. Now it turns out that for it's a self-study thing. I want you to figure out what that. So good suffix values have been computed. All I have taken is take the pattern, reversed it, compute the zi values, and reverse that array of zi values. You get z suffix values, and then from z suffix values, I've used the algorithm pretty much from 7 to 9 to nail it. Now, I want to pause one thing, flag one thing about the pseudocode. Can you please look at line 3 of the pseudocode? What's the range? 1 to m plus 1. That's a bit weird. Now, there's no reason for you to have it to initialize greater than the string length. The string length is a pattern, right? Pattern is m, there are only m characters, but you have m plus 1 there. Now, can you see what happens to line 8 if the z array value is 0? When the length is 0, when you don't have a z array defined, what will be line 8? M plus 1, m minus 0 plus 1. Essentially, you can avoid that extra cell, m plus 1, if you had this specific conditional branch, if-else statement. If z suffix of if z suffix of p equals 0, or rather, you would only run line 8 if z suffix of p is greater than 0. If you had that if statement, if that you had that conditional branch, then you don't need that extra cell. So what Gus Field has done is by creating that extra dummy cell, m plus 1, he has taken away the conditional branch. Now, if you actually have, remember, do you do any assembly these days, assembly language? If you assemble your, if you basically take your high-level code, disassemble it, and then see what happens to machine instructions with a conditional branch and without a conditional branch, you will see that this will run imperceptibly faster. It doesn't make any practical difference. I would still advise you to write it with an if statement because it's clearer code. But I just wanted to still give that excitement that, well, you could do some simple tricks and do away with the if statement. All you have to do is an extra m plus 1. Okay, is that clear? What I've done there? Or what Gus Field has done there? All right, so if that thing is there, how do I use the good suffix rule? My good suffix will tell me where the matches are. The green boxes align. So the mismatch is at position k plus 1 to m matches. Now when I look for good suffix of k plus 1, it will tell me the rightmost occurrence of k plus 1 to m in the pattern that's not itself. Rightmost occurrence that is other than the instance. Rightmost, so k plus 1 to m, it has to be the rightmost because that's a good suffix. Other than that, where do I find that alpha? Well, if it found that alpha, good suffix of k plus 1 will point to the position p, wherever the p is, where alpha ends in the pattern. And when you shift it, you are making sure that the character at p lines up with the, so character of p will take the position of where the character m is, so after shift. That's all you're doing. Okay, good suffix is to process it. You can process it and pre-process it in linear time. By the way, you're not doing it in every iteration, you're pre-processing it, right? You don't, that's the whole idea. The idea is that you have bad character tables and a good suffix tables done even before you start the iterations. And then you're simply using it. And so, how do you know how many positions to shift by? Well, p has to occupy where the current m is. So how many positions should I shift by? M minus p, but p is nothing but good suffix of k plus 1, so you're shifting by m minus good suffix of k plus 1. What is that k plus 1? It is a symbol that tells you that k is where the mismatch is. The definition of a good suffix starts from k plus 1 to m. All clear? Okay. Now, what happens, and this was a question one of the audience members raised, what happens when good suffix alpha does not exist? And I said you have to shift past k, right? That's what I said. Why not m? Okay, now take a look out here. So I had in some iteration this matched with this matched with this matched with this matched with this, right to left scanning, and then this does not match with this. The good suffix is BACABA. Okay, does BACABA appear anywhere else in the pattern? Pattern is this one. BA, good suffix is BACABA. Does it appear anywhere else? No. So where do I shift by? Look at that blue boxes. So there is, if I didn't find k plus 1 to m to map, I didn't find an instance of k plus 1 to m anywhere else in the pattern, I have to look at a smaller suffixes of k plus 1 to m. So k plus 2 to m, does it appear? K plus 3 to m, that appear. And if it appears, it has to appear such that it matches the prefix. So it's not any occurrence of k plus 2 to m or k plus 3 to m. It is the occurrence which matches the prefix. So there's some proper suffix of k plus 1 to m. Proper meaning that it is of size less than k plus 1 to m. Proper set, subset. Proper subset in mathematics is always a subset that's not itself. Okay? K plus 1 to m you never found. The scenario is you didn't find k plus 1 to m. So proper suffixes of k plus 1 to m would be k plus 2 to m or k plus 3 to m all the way to m to m. So what would be the longest proper suffix of alpha, the good suffix k plus 1 to m, that matches the prefix? Okay? It is not any occurrence, but the one that is longest that matches the prefix. So it's a much more stricter condition. Now, it turns out that the longest proper suffix of that green box, so it has to be ACABA matches AC, does it match? Sorry, the prefix is ACABA. Do you see that it matches there? The blue box matches. I mean, it could be the one after that. The longest could be, if the longest is 0, what would you do? You shift past m, right? If it is 1, you line it up so that it aligns with m. If it's 2, it lines up to aligns with m minus 1, and so on. So you have to find while you are computing the good suffix, you can pre-process also. In fact, it's a tute question this week. If you go to the tute question, one of the question would be find the suffixes that matches the prefixes. So if you look out for the tute question, if you did that tute question, you would get match prefix array computed in linear time. So essentially what I'm trying to get at is good suffix can be computed in linear time, match prefix can be computed in linear time. Good suffix is a much more general computation because you're looking for the rightmost occurrence of any substring ending at a position that matches the suffix. That's a much more general one. Match prefix is far more constrained. It's saying that what is the suffix that matches the prefix? Okay, what is the suffix? The longest suffix that matches the prefix at any position. At any position from 1 or 2 or 3 all the way to m. Now, if you had pre-processed it, if k plus 1 to m gave good suffix of k plus 1 to m, the green one gave 0, then you say what's the longest, what would be the matched prefix from k plus 2 to m, okay? So k plus 2 to m match prefix implies that it's a proper suffix of k plus 1 to m, and then what's the longest suffix of k plus 2 to m, which is a proper suffix of k plus 1 to m, that matches the prefix. It will have a value, and if the value is greater than 0, you essentially shift by m minus the match prefix. So you're essentially doing the same rule based on, you're doing m minus match prefix of k plus 1. Well, I'm conditioning it as k plus 1 because k plus 1 to m is exclusive of these suffix k plus 1 to m, because good suffix of k plus 1 to m you never found. The match prefix of k plus 1 to m would be k plus 2 to m, or 3 to m, or 4 to m, or 5 to m. So although I'm calling it match prefix of k plus 1 to m, really what you're trying to compute is the longest prefix of the longest suffix starting at k plus 2 to m, or k plus 3 to m, or k plus 4 to m. What is the longest one that matches the prefix of the same length? Okay, think about that, and then self-study, see why for this example, the same example, we saw these two previously, z suffix values, the good suffix values, and this is the match prefix values. In fact, it's fairly simple once you work out on pen and paper, work out an example why that's the case. I'll get you to do that in your self-study, and also we will do that explicitly in your tute. Okay, that's a good tute exercise rather than something that we have to handle in the lecture. But all these things, linear time in the size, you can pre-process the pattern in linear time to compute all these three things without a worry, without even seeing the text. Now, we have done the case where when bad character happens, you are shifting by a certain number. When good suffix happens, good suffix rule tells you to shift by a certain number, either by m minus good suffix of k plus 1 or m minus match prefix of k plus 1. If the good suffix of k plus 1 is 0, you have to use match prefix. All this is okay. There's only one scenario we haven't yet considered. Okay? What is it? It's a scenario where there's no definition of a good character or a match prefix, when everything matched. Okay? When everything matched, what do you shift by? I'm going to write an example on the board, and maybe you will see what the logic of what you shift by is naturally inherent. You don't have to calculate anything extra. You already calculated, pre-processed some things up to now that you could use to do the shift if it's the whole thing matched. Okay, let's take the pattern to be A, B, C, A, B, C, A, B, C. Okay, that's the pattern. So 1 to 9. In the text, that's the text, that's the pattern. A, B, C, A, B, C, A, B, C. Let's keep going a bit more. This is a periodic string that I've given an instance of, and the periodic string has a period of 3. ABC repeats itself, right? This matches with this, right to left scan in this iteration. Everything matched, right? Has everything matched? Now, if everything has matched, you would first say, ha, I found an occurrence, remember that. Because the goal of all this is to find an occurrence of each pattern in the text. Now, how many positions do you, my question is fairly simple. How many characters to the right do you shift pattern by in the next iteration? One is an hypothesis. Anybody else? Anybody wants to tell me?
In this case would be 3, right?
So the suggestion was 3. So one was one. Hypotheses are 1, 3. Anything else? 9. Okay, so 9. Now we can rule out 9 straight away, because can you see that we will be missing other occurrences if I shifted by 9? So if I said ABC, ABC, let's say there was a ABC, well, it could have found that instance, but it didn't find an instance of ABC, ABC, ABC here. It didn't find an instance of ABC, ABC, ABC here. So 1 is safe, 3 is safe, 9 is not safe, so we'll rule out 9 we'll not consider that as a hypothesis. So you'll see that really anything other than 1 and 3 either will give you a sure mismatch or you'll miss something. Okay? So one is basically naive. So it always is a hypothesis, always there for every iteration. But 3 seems promising. Is there anything that we have computed that allows you to shift by 3 straight away? Yep. Z values, we computed Z values, but Z values, I think it's the Z values is sort of an intermediate step. You really have 2 data structures that you're maintaining, good suffix and match prefix. So which one of good suffix and match prefix would you think you should use to shift? So match prefix is always going to give you a relationship between the suffix and the prefix. Okay? Good suffix. If you say good suffix of what position though? Because it's a function of the position, isn't it? So good suffix of k plus 1 is what we were using. So clearly we don't have a position of anything to go by, because if you say good suffix of 1, it kind of doesn't get you anywhere. Now I want you to focus on matched prefix. So match prefix of 2 will contain the longest match prefix of 2 will contain the longest proper suffix of 1 to m. So if the mismatch were at 1, let's assume hypothetically if the mismatch was at 1, the proper suffixes would be 2 to m, 3 to m, 4 to m, and so on. So match prefix of 2 would basically essentially contain the longest suffix from 2 to m or shorter that matches the prefix. So if you look at look at those characters 2 to 9, okay? Let's ignore the first one. What's the longest suffix inclusive of 2 to 9? So 2 to 9, 3 to 9, 4 to 9 that matches the prefix. What's the length of the longest? What is the length of the longest 2? So 2 would be BC. Longest suffix that matches the prefix. I heard 6 there. 6 is that matches the prefix. ABC, 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 ABC matches ABC, ABC, right? So longest suffix starting at position 2 that matches the prefix. So clearly it can't be you can do it naively. BCABCABC, does it match the prefix? No. What about CABCABC, does it match the prefix? No. Next, ABCABC, does it match the prefix? Yes. How many letters was that? How many characters were it? 6, right? So if you shift by, so what do you shift by? So your total length was 9. If you subtract that with the match prefix of 2, which is 6, or rather m minus matched prefix of 2 is 9 minus 6 is 3. 1, 2, 3, I have ABC, ABC, ABC. Okay? So whenever you get a full match, all you have to do is apply m minus match prefix of 2. Okay? Now it turns out that this is for periodic string. If it's not periodic, even better. It will say shift more. If let's say you didn't find anything that matches it, it will shift by entire 9 or the m letters. Okay? So now we saw all the cases here. So the case is, where is that? Sorry. Your shift by m minus match prefix of 2 is what we have reasoned why when everything matches, you apply that. Now that kind of sort of concludes the business end of Boyer-Moore. Now pre-processing, you have to pre-process the pattern even before you see the text for either bad character rule or extended bad character rule. So it's one single array for bad character or a table for bad character. That's one thing that you have to pre-process. You also have to pre-process good suffix and match prefix using the Z algorithm that I talked about. Once you do that, your algorithm scans starting from the first position of the text, align the pattern, do the right to left scanning. It defines a good suffix and a bad character, and the good suffix and a bad character is used. Each of them says shift by some number of positions. So let's say bad character says shift by certain number of characters. The good suffix says shift by a certain number of characters. Both are going to be safe. They're guaranteed to be safe. You choose the maximum of the two. If both are safe and two experts say different numbers, you are safe to choose the largest shift of the two because both are safe. Both are guaranteed to be safe. So if you did that, you have to do a max of those two things and you're in business. Now, only thing that you have to keep in mind is this beautiful optimization. I think in the literature, you'll find words like Garil's optimization, but all the words appear much more, when you have a named algorithm, it appears much more sophisticated than it really is. A simple thumb rule is when you shift, what are you shifting? You're shifting such that certain characters have to agree, right? And you know in between shifts that they agree. When you know they agree, do you have to recompare the characters? If you know they agree, you don't have to recompare when you're doing a right to left scanning. So think about this. Alpha matches with alpha. Then there's a bad character that says, for instance, X and Y. You found some alpha such that the preceding character is not Y. So I'm calling that character Z. In fact, if you could have actually done the algorithm by saying the preceding character has to be X, whatever the bad character, which means that the good suffix is no longer a single dimensional thing, it is a multi-dimensional thing. Just like an extended bad character rule, you could have an extended good suffix, but we're not worried about that. What we have done is alpha matches with alpha, the occurrence of alpha ends at P, and then when you shift it, alpha lines up with alpha. I know that this alpha and this alpha has to be the same because that's the way I shifted it. So when you're doing a left to right scanning, I don't have to compare characters in that region to be same as that. So you're doing a left to right scanning, let's say that match, 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 match. So that matches with that, the opposing characters match all the way, left to right scanning in the next iteration. The moment you come to P to the one before, P minus M plus K plus 1, that whole region has to match in that region, so you skip. You just need to have two pointers that tell you the regions that agreed in the previous iteration. You ignore those regions and then jump straight to this character and say, well, does X match with Z? If the answer is yes, keep continuing. And if it matches the whole thing, now look at this scenario here when it matches the whole thing. Do you have to match these characters again? So if you're doing match, 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 I don't have to match any of these because the way I've shifted this, right? So this matches with this matches with this matches with this, but I know that this region has to match with this region because that's how I shifted. I don't have to compare this. So every iteration, don't repeat any matches that you know certainly match is the optimization that you have to apply. A very simple optimization, right? All right, so the idea would be that you just need to hold start point, end point for each iteration, and then if in each iteration that start point, end point gets updated, and then you don't ever recompute the thing for when there's a good suffix shift or even a match prefix shift. So full match is a match prefix shift. There are So you get a match prefix shift for two reasons: when good suffix is missing, or if the pattern matched the region in the text. So in both cases, you would basically be using that. Now, KMP, so I'm in two minds whether I should talk about, okay, I'll very quickly talk about KMP, and maybe if it spills over to the start of the next lecture, I'll continue from there. I think we've got 5 minutes. So it's a very simple algorithm which is so easy after going through Boyer-Moore. I must say that this is not a practical algorithm. The go-to algorithm would be Boyer-Moore, but I really wanted to sort of connect the full circle on this thing. KMP was one of the classics in computer science. With Z algorithm, it's very easy. Now, it is shifting the pattern like Boyer-Moore from leftmost ends to, so you're shifting rightwards pattern, but rather than comparing right to left scanning, it's doing the normal human way of doing it, left to right. So what it ends up doing is saying, I want to find out for every position I, so there's a pattern 1 to m, for every position I, what is the longest proper suffix of 1 to I? It appears as if it's similar to what we just discussed, but it's not, it's subtly different. What is the longest proper suffix of 1 to I? Not the suffix of I to m, which is what we are talking about in Boyer-Moore, but here it's 1 to I. What's the longest proper suffix of 1 to I that matches the prefix? So the proper suffixes of 1 to I are 2 to I, 3 to I, 4 to I, all the way to I to I. And the modern variation of it, I mean, original thing was that was all they cared about, KMP, Knuth, Morris, Pratt cared about. But the modern version with Z algorithm is that added constraint that what's the longest proper suffix of 1 to I such that the characters after the match are different. So I plus 1th character is different from whatever character that matches the prefix, it comes after the prefix sign. So if you look at that, so 1 to I has some, so length is SP of I. SP is the longest proper suffix of 1 to I that matches the prefix of the same length, so that yellow boxes are of the same length. The characters that comes after Y are different, okay? Now, that's what that condition means. Now, why do I care? I'll come back to this slide in a bit. So I'll come back to that slide. So what you're doing in KMP is quite simple. So you're comparing, so you're at position, some intermediate iteration, you have match, you're doing a left to right scan, match, 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 at position there, the match, the last match was found, the next character was different. When the next character was different, what you're trying to find is what's the longest proper suffix in that green box that matches the prefix. So what's the longest proper suffix? So it is basically that yellow boxes, what's the longest proper suffix in that green box that matches the prefix? Once I found that, I would just shift such that the yellow boxes line up. Okay, it's like, it is like the shift, there's nothing more to it, just by saying what's the longest. All the magic is how do I find the SPI value for a given pattern. You can pre-process it in time proportional to the pattern length, OM time, and the shift is basically going to be I minus SPI is a shift, basically. What you're trying to do is you kind of, I minus SPI value is the shift that you have to do, and if it matches the full one, if the whole thing matches, you have to do M minus SP of M. So I minus SP of I, when you match the whole thing, it reaches M, isn't it? So I minus SP of I will become M minus SP of M when everything matches. Now I'll just very quickly go back to that slide that I said, we'll come back to it. I want you to look at the definition of SP of I for that pattern. Just stare at it. We got a few more minutes. Just stare at it. I want to just flag. I want you to mainly reason, what is the SP of 9 correct? The longest proper suffix of 1 to 9 that matches the prefix. Is that correct? 3. So at position 9, that's the position 9. What's the longest proper suffix of 1 to 9? So 1 to 9 is 2 to 9. The 2 to 9 match the prefix. It's a mismatch, isn't it? 3 to 9, does it match? No. If you kind of keep coming all the way to BBC, that BBC match BBC, the prefix. But what's the character afterwards? Does A match C? So it has to be, the characters after have to be different, so the answer is 3. Now, but take a look at 8 now. What's the longest proper suffix of, at position 8? Why is it not 2? Why did I write 1? Correct. So if you ignored that condition that a characters after don't match, if you're at position 8, the proper suffix BB matches BB, but the character after C has to be character after C. The reason why they should be different is because you don't ever want to shift such that you again get a bad character in KMP or whatever, the mismatch in the KMP, because you want that character to be different. And so it is not 2, it has to be 1. 1 is basically going to be, so if at position 8 it's just B matches with a B, the next character is a B, the next character after that is a C. So it holds that condition. So, and all you're then doing is the computation of, it's very similar to the computation of how you compute what you have done previously, except that you're now going from M down to 2 rather than, so you're doing it with respect to Z values. So you're using Z algorithm, you go backwards because you want to find the longest. So you have to keep replacing it with longer and longer suffixes. When you go backwards, you get longer and longer suffixes for any given